everyone. In the last video, I had covered all the topics related to probability distribution. But imagine you have so many probability distributions. How you will analyze them? One by one each? No. So you will group them up into single value and which is called as expectations. So just now I studied about what expectations are and how to work in them. So I will just try to present it today. So let's begin. Okay, so think of expectation as a simple engine behind many machine learning algorithms. So whether we are minimizing loss function, computing averages, estimating parameters, or computing neural networks, expectations appears everywhere. So the balance is intentional. So it represents the idea that expectation is center of probability. Okay, it's the center of probability mass, not necessarily the point with the highest probability. So let's begin. First, you will have the question that what expectation actually does. So one way to think about expectation is as compression algorithm. Now imagine replacing the entire probability with a single representative number. Instead of storing thousands of possible outcomes, expectation compresses all of that information into single value. So this compression is extremely useful because it makes calculation easier for us, right? Now, notice that expectation is shown as center of mass, which is a physical interpretation. If the distribution were made of metal, expectation is exactly the point where it would balance. Okay. Now, there is a important misconception that is like expectation is always most likely value, and it is not true actually. So just remember this thing. Example how to okay. Just think of example like consider income distribution, and most people earn less than average income because a small number of extremely high salaries pull the average upward, right? Like the GDP of India also. Now, point to infinite horizon. Now, hmm. So in this, if we repeat an experiment many times, the average of observation gradually approaches the expectation. So this is why expectation represents the long run average. Now, moving on forward, let's see the mathematical definition about PMF and PDF first of all. So, since we have already studied PMF and PDF, these equations should look familiar to us. Now, for discrete random variables, we multiply every possible value by its probability and add everything together. And for continuous random variables, the summation becomes integration. Simple. Now, there's an important observation which you should do, which you should see is like um this x into p of x or x into f of x, every value contributes, but larger probability contribute more strongly. Can you understand? Like larger probability contribute more strongly. That's why expectation is called a probability weighted average. Okay, so remember this. Why expectation is called as probability weighted average? Because larger probabilities contribute more strongly. Now, one important condition is that expectations must be finite. Like some probability distribution have extremely heavy tails now. Although probability exists there, but their expected value may not be there. Okay. Now, we know about how expectation is defined. Let's look at the mathematical properties now. So, there are three pillars of operations. Instead of memorizing this all formulas, just everything we will use comes from these three fundamental properties. Okay, so just remember these. Now, the first property is linearity. It allows us to simplify complicated expressions immediately. Then there is second property which is lotus, the law of the unconscious statistician. Now, despite of this name, it provides a shortcut that avoids finding transform distribution. Now, the last is tower property. Finally, the tower property simplifies nested expectations by computing them step by step. Now, together, these three ideas form the computational toolkit used throughout the statistics and machine learning. So, let's begin with the most important property, linearity. Okay, so the most remarkable property of expectation is its linearity only. Instead of reading the equation, just you can think it like the expectation of a weighted sum is simply the weighted sum of the expectations. I will repeat it. The expectation of a weighted sum is simply the weighted sum of the expectations. Now, constants move outside the expectation unchanged. Only the random variable remain inside. Now, the surprising part is shown on the right, like expectation remains linear. Whether variables are independent, dependent, positively correlated, negatively correlated, independence is not required here. Okay, so that's what makes this property very much powerful. Now, the only requirement is that the expectations themselves exist. Means, let's see why this property is so useful to a probability problem. So, suppose there are n people randomly assigned to n seats. Now, on average, how many people end up sitting in their own seat? And solving this directly is surprisingly difficult because the events are dependent. So just instead we define an indicator variable now. So it is equals to 1 if person 1 if a person I gets the correct seats, and otherwise it's 0. Now the expected value of each indicator is simply the probability of that event, which is 1 by n. Okay, now the final equation. Now, linearity does all the work. Instead of solving a complicated combinational problem, uh, we, sim- uh, we simply add the expectation. Everything cancels very much nicely, and giving up that e of x equals to 1. Now, linearity transforms an extremely complicated counting problem into two-line calculation. And the second pillar, which I told you, provides another shortcut. But this time for transform random variables. Let's see. Recall from the previous lectures that when transforming a random variable, we usually needed to derive the distribution of transformed variable first. And that was a, what we say, mostly, not mostly, it was a traditional approach. Now, find the new PDF, then compute its expectation. Okay. Now, here comes Lotus. LOTUS tell us that this entire process is unnecessary. Instead, we keep the original distribution and simply replace x with the function gx. Okay, so here we want ex square for a uniform random variable. The traditional method requires deriving the PDF of y equals to x square, but Lotus skips that completely. We integrate directly x square using the original distribution. Now both methods give 1 by 3, but Lotus is much faster, of course. So this Lotus saves the work by allowing us to compute expectations of transformed variables without deriving the transform distribution. Now moving on to next thing, like we have covered first two pillars, and the final pillar is the tower property, which shows how expectation can simplify multi-stage probabilistic system. Like um, just a second. So here you can see the formula. The overall expectation is equals to the average of the conditional expectation across all the subsets of Y. So this was about the tower property. Now moving on forward, these are three things like where intuition fails, where we can make mistakes. So you cannot just take expected value of x and plug it into a function. For example, the average of x square is not equal to square of average of x unless x never changes. So if you roll a die, even x is equal to 3.5. So e of x square will not is equal to 12.25. But the average of the squared outcome, e x square is equal to 15.17 something. Okay, so I went too much mathematically. Just simply, like this is no this thing which I said is known as Jensen's inequality, and the only time you can pass the expectation inside a function is when the function is a straight line. So that is the thing. Now, multiplying versus adding variables. Like this time, this mistake we make commonly. So just remember that addition means works always, whether x and y depend on each other or not. But multiplication only works if x and y are independent. So if one variable affects the other, multiplying their averages will give you the wrong answer. Moving on forward. Hmm, yeah. So moving on forward, there's one more thing, confusing expectation with most likely or typical things. Okay, so thinking that expectation is a number you will see most often, that is the wrong thing. Expectation is just the balance point, center of mass of all possible outcomes. Okay, now next thing is like integrating or summing over the long range in Lotus. It is mostly done in Lotus. Okay, so when using the law of unconscious characterization, which is Lotus, to find expectation, changing the limits or domain to match gx instead of x. Okay, remember it. In reality, when you compute expectation, the limit of the integral must cover all possible values of x, not the values of g of x. Okay, next thing is like assuming every distribution has expectation, like expecting every random variable to have a valid or finite mean. Some probability distribution have heavy tails, and like it's like that is extremely rare. But for the distribution like Cauchy distribution we have heard, so the integral or sum does not settle down to a single finite number. The average value simply does not exist. Okay, now the next thing comes why we are studying this. So it's all like we use this in machine learning so much, like empirical expectation is equals to sample mean. This is like done in LLM. This topic will come after a few videos. And every training loss is an empirical expectation over the data set. Second thing is like expected loss or risk. For that, it tells us very like it gives a very what we say empirical risk minimization approximation. This approximates this with the sample mean. Okay, the next thing which it helps in like policy gradient, and like gradient of expected reward reinforce estimator using Lotus, plus finds the linearity to push the gradient inside the expectation. And last thing like indicator trick, this which is used in machine learning theory constantly. So it is just example expected number of misclassification. So this formula is used there also. So that's all for this video. If you find any kind of improvements from my side or mistakes in the current video, you can just say me down. Bye bye.